So, we took a look at the spring oscillating, or a mass oscillating on a spring just a moment ago. We're going to go through and try and take a look at the other simple harmonic oscillator, which is a simple pendulum that has been moved by a very small amount, theta. Now, you're going to see a lot of stuff listed, and I mentioned it in class that it's basically a little bit of housekeeping. But normally we say that this is only applying when theta equals a small value, small angle. You're going to see that's going to be part of our derivation. In short, if you have a small angle, something that's like 5 degrees or less, I keep track of it in degrees because I'm used to thinking in terms of that. I don't even remember what the radian equivalent of that is. But if you take 5 degrees, convert it into radians, and then put that number in through a sine of theta, pay close attention to it, and you'll find that you get pretty much theta back out. In fact, for 5 degrees or less, I think it's accurate to 3 or 4 significant figures, which is higher precision than we usually go to. You'll also find that cosine, now all of this is in radians. Convert the angle to radians and set your calculator to radians so that you can get the actual result. But cosine of theta is going to be equal to about 1, and tangent of theta is equal to about theta because it would be sine divided by cosine, which is theta divided by 1, which is just about theta. So whenever you're dealing with something in engineering that is called small angle approximation, this is what they're doing. They're relying on the fact that if theta is very small, that you only have slight nudges, then sine of theta is actually going to be equal to pretty much theta. Tangent of theta will be equal to pretty much theta. And cosine of theta will be equal to 1. It's accurate to, or I'm sorry, depending, if you have a very small angle, it's pretty precise, so it's only a slight approximation. And it saves you a lot of time and effort. One of the ways that we're going to see that is coming up. All right. Now that we've got that out of the way, let's talk about the pendulum. There's one other thing that I want to bring up. For the pendulum, we're going to deal with a small angle approximation, and one of the things to keep in mind for a pendulum is that if I take this pendulum and I move it ever so slightly, it doesn't really do much moving in the y direction. We're going to see in just a little bit that we're going to basically approximate its motion in the y direction to be 0. It's not exactly 0, but if it's a very tiny number, then we can treat it effectively as 0, and that's more or less what we're going to do. Now, to work with a simple harmonic oscillator, we need to use its equation. The simple harmonic oscillator equation, as we've seen before, is omega squared times the position function plus the acceleration equals 0. Technically, it's omega squared x plus x double dot equals 0, where each dot represents a time derivative of the position as a function of time. We're going to use this way of writing it because it's a little more convenient for us, but they're both saying the same thing. All right. So what we really need is something that describes the position, and we need something that describes the acceleration. All right, let's start with the position. I've got a 0 point here, and I'm going to draw the pendulum over to this point where we have theta. Now, what we're going to deal with is this. We've got that this length is L. And since we're dealing with a small angle approximation, it turns out that this length is also L, but that's okay. What we're going to do is the following. If I want to keep track of my x position, with this being 0, my x position over here is some negative x. I'm going to say that this is theta equals 0 as well. Now, this will also swing back over here to positive theta, but that's okay. We've got a triangle where we've got an x and a y, and if I set this up, my hypotenuse being L, I'm going to get the following. That, with this being the opposite side, we have sine of theta, sine theta equals opposite over hypotenuse, is going to be equal to x, our x position, divided by L. Now I'm going to take this one step a little bit farther. Here's where the small angle approximation comes in. Sine theta can also be approximated as theta. And one of the nice things about this is, if I have a negative theta, then this would be negative, and I end up with a negative x, which is what I need, negative x. If theta is positive, and I'm over here, then we end up with a positive x. All right, so here's where I get the following. I can write that x, my position function, is equal to L theta. Now I've got something as a placeholder for my position function. It's L times theta, where theta is a small angle, and we keep track of where theta is. We plug in theta, and that gives us our position. Now, we would have a function where theta is actually a function of time, in case you're wondering about that. Theta is not constant, and as time goes forward, theta is going to move back and forth, and it will be directly related to x. So it's an easy way for us to parameterize and keep track of what's happening position for our linear position. All right, let's take a look at the next part. This one's going to be the trickier part. We've got the pendulum like this. We're going to have it over here in the negative area and at some angle theta. We need to find, we've got its position, now we need to find something for the acceleration, so a great place to look, if you're looking for accelerations, is Newton's second law. And we're going to look in both the x direction, sum of forces in the x, and the y direction, sum of forces in the y. Let's start with the y. You'll see why I'm doing that here in a moment. Just so we've got this clear. The force that's acting on the pendulum is a force of tension, Ft. Now, that force of tension has components. Here's the y component. I'm going to save a little bit of writing and call that Ty. Here's the x component, which I'm going to call Tx. In fact, we've got it set up pretty quickly and easily. Oh, by the way, by geometry, these two angles are the same, theta. Sum of forces in the x, that one's easy, it's Tx, and that'll be equal to our mass times our acceleration in the x. But we're really only looking in the x direction, so I'm just going to call that the acceleration. The reason why, and think back to what I showed and mentioned a moment ago, when it's nudging back and forth like this, there's very little y motion. So when I do my sum of forces in the y, I get the following. Ty, positive, it's up, minus mg, the force of gravity, downward, equals about 0. It's technically not 0, but for a very small angle, there's almost no motion going on in the y direction at all. All right? I can add this over and I get the following. Ty equals mg. Tx equals ma. Here's where things are going to get a little bit trickier, but we've got a resultant vector, Ft, and it is made up of the x component, Tx, and the y component, Ty, with this being theta. I'm going to write down two relationships real quick and then quickly change them into what we need. Tx equals Ft times, opposite sine theta, and Ty is equal to Ft cosine theta. Now I'm going to change them into what we need because I need to start getting some replacements in so I can get the acceleration by itself effectively. Here's what I'm going to do. I'm going to turn this into Ft is equal to Tx divided by sine theta. Oh, I'm sorry, that one's probably not actually needed. You'll see why in a moment. Tx is actually what I'm looking for. What I need to do is I need to convert Ty in that way. So, Ft is equal to Ty divided by cosine theta. I apologize. You can do that replacement up there, but it's not actually going to directly help you. The reason why is this. Tx equals Ft sine theta. That's this equation here related to this triangle. But Tx is also equal to the mass times the acceleration, and I want the acceleration. Here's why we needed Ft, because if this is Ft, we can plug it in for Ft. And we get the following. Just ignoring tx in this altogether, we replace ft with ty over cosine theta. We'll see why that's useful in a moment. I cut out one useful step. Times sine theta equals ma. The other thing we need, ty was equal to mg. Sum of forces in the y direction. So I now get the final equation here. Ty gets replaced by mg divided by cosine theta times sine theta equals ma. Well, the m's cancel out, and sine divided by cosine, I get the following. G tangent theta equals a. And for a small angle approximation, tangent theta is pretty much equal to theta. So g theta equals the acceleration. All right, here we go. Finishing up. Omega squared times our position function plus our acceleration equals 0. I'm going to start plugging things in based on what we've got. We end up with omega squared times our position we said was L theta plus, let's see, I apologize, one quick thing that I've overlooked here. If theta is positive, in other words, if we are over here, positive theta, the acceleration is negative. And if theta is negative, the acceleration is positive. One thing that we actually need for our acceleration is a negative sign. All right. Negative g theta. This is the acceleration. This is my position function. And for a simple harmonic oscillator, these should come up to 0. Okay, so here's what I'm going to do. Omega squared L theta. I'm going to add this over to the other side equals g theta. So that negative takes it over to the other side. Thetas actually drop out. We get the following. If I want to solve for omega, we get omega squared equals g divided by L. And hey, look at that. Omega equals the square root of g divided by L. Now remember, and this is that little bit of housekeeping, all of this derivation happened because we could then change this over to theta. And more specifically, we assume that almost all the motion is in the x direction. That's really only going to happen for a pendulum if it's dealing with a small angle of oscillation. If it comes up to a high angle of oscillation, we end up with a noticeable change in what's happening in the y direction, and this no longer holds, which means our equations would have to be adjusted. This is why this one is described as the natural frequency for a pendulum with a small angle.